Hi, this is Tony Northrup for Train Signal, and in this video lesson I'm going to talk about networks for the Sscp certification exam. Up first, I'm going to cover a couple of common logical models that are very abstract and not necessarily related to the real world, but they are the kinds of things that you'll see in the certification exam, and it's also helpful to understand the kind of academic models when you discuss networking with your peers. This is the OSI model, the Open Systems Interconnection model, and it has 7 layers. Now I'll start from the bottom up here. The bottom layer, layer 1, is physical, and these are the physical wiring or wireless protocols that are used to actually transfer the electronic communications from one device to another. So this is your Cat5 or Cat6 cable that you plug into the Ethernet, and the specifications for how the wires are wound together and the distance between the pins and the size of the head, that kind of thing. For Bluetooth, the layer 1 physical standards specify the maximum and minimum power of the radio device and the frequencies that it uses. The same thing applies for Wi-Fi. If you use home Powerline Networking, HPNA, the physical standards specify exactly how it connects in and the frequencies that it transmits across the wires itself. So as you can see, layer 1 standards specify the physical properties of the electronic communications. And as we go through each of these 7 layers, there are going to be standards that work at this specific layer. And only by making all of these standards work together can we actually communicate across a network. So layer 2, the data link layer, is the formatting for the messages across a local area network. So there's no routers involved. This is all within your home or within your office. These are devices that are physically within range, able to communicate across some kind of media. So something most layer 2 protocols have in common is working out how to detect and avoid collisions. So if you imagine that there's a layer 2 protocol for just talking to your friend with your voice, well, you wouldn't talk over each other, right? But we as humans kind of look at each other and we make eye contact and we figure out when the other person's going to talk, and we wait and we take our turns. Well, the same thing happens in networks, and all of that happens at the data link layer, layer 2. So in Ethernet networks, it's possible, if you use a hub rather than a switch, that 2 people will be communicating on the network at the same time. So the data link layer protocol standards for Ethernet specify waiting, and if you hear a collision, pausing for a random amount of time and then starting again. They also specify addressing other hosts on the LAN by using their MAC address, which is the address of the network adapter. So that type of thing happens in layer 2. Layer 3, the network layer, starts to take into account routing. So here we introduce IP v4 and v6. If you look at the IP standards, what they add over the data link Ethernet standards are the IP addresses. And these IP addresses, well, they're not necessary to communicate between 2 hosts on a LAN. That's handled at the data link layer. The IP address is required to route it from one network to another, and then finally to the host on the LAN. And that's why IP exists at layer 3, because this is the network and combining multiple networks together, but not 2 hosts communicating on the same LAN. Layer 4 adds more reliable communications to layer 3. Layer 3 gets you from one network to another. Layer 4 detects packets that have been corrupted in transit and allows them to retransmit if you're using TCP. Both TCP and UDP standards that you might be familiar with, they both exist at the transport layer, layer 4. And they both include checksums, just to allow the recipient to determine whether the packet was changed or modified in transit, at least not deliberately changed. Somebody could still maliciously change the packet and then update the checksum too. The difference between TCP and UDP is TCP will automatically retransmit corrupted packets. UDP just doesn't bother retransmitting. Now we move up to layer 5, the session layer. This starts to get really more abstract, and it's even hard to find tangible examples of layer 5 and 6 protocols because they're more theoretical than practical. But what you see at the session layer are long-standing connections between 2 devices that might span multiple different TCP connections. So if you're familiar with old style Windows file sharing, sometimes called NetBIOS, Two computers will establish a connection, and they can use that same connection for days or weeks. They can use it for file sharing or computer management. A lot of different things happen in there, and that makes NetBIOS a session layer protocol. Other applications are working above it. File sharing could use it. Computer management could use NetBIOS. And other things like TCP are working below it, so it's kind of in the middle between the transport and the application. The presentation layer is probably the least frequently used layer in practice, and the only example I could really find that anybody might be familiar with is MIME. That's basically a standard for encoding messages in different formats. So you can use MIME to specify that a message is encoded in text or compressed, or that it's a video file or an audio file, that kind of thing. The presentation layer is just meant to provide some formatting for the top layer. The top layer being layer 7, the application layer. And this is really where the good stuff happens. This is where the work gets done. So here you have HTTP for web pages and web services. You have DNS for resolving names. You have DHCP for assigning addresses automatically. You have IMAP and POP for retrieving mail, and hundreds of other application layer protocols. So OSI was a model that was developed 40, 50 years ago when networking was still kind of being pulled together, and they were planning it out on a very theoretical level because these are engineers and they had to come up with a way to break a big problem down into smaller problems. So they said, well, let's break it into a series of 7 layers, and then when we actually go to write the code, we just need to deal with one layer at a time. And we'll kind of specify transitions between the layers. So the guy who's working on the data link layer standards doesn't have to fight too much with the guy who's doing the physical layer standards. So we kind of draw these lines of demarcation, and that makes it easier to divide up the work because, of course, hundreds of thousands of different people have worked at separate layers over time. Now let's look at the IP model. While the OSI model is definitely the most frequently cited and it's the most important one for you to be familiar with, I think the IP model makes way more sense. The IP model has 4 layers that you see in the middle of this table here, and they roughly map to the OSI model, though they don't directly map. Layers 1 and 2 of the OSI model are wrapped into the network access layer of the IP model. So the network access layer would include the specifics of the cabling that you use for Ethernet, as well as the fact that you address other computers with MAC addresses and the way that you do collision avoidance on the network. The internet layer maps pretty directly to layer 3 of the OSI model. It specifies IP and sometimes ICMP, which is used to kind of communicate errors and routing problems at the IP layer. The transport layer of the IP model, conveniently, maps to the transport layer of the OSI model. I don't know how we got those guys to agree on that. That's about the only place they did perfectly agree, but it works out well. So you have TCP and UDP at the transport layer. And then, and this makes a lot of sense to me, the application layer of the IP model maps to layers 5, 6, and 7 of the OSI model. It just takes all that stuff and crams it in together. And this models pretty closely how most applications are actually written. Nowadays, if you come up with a new protocol, let's say you're developing the next web server and you want to come up with whatever the successor to HTTP is, well, you don't write a session layer protocol and then a presentation layer protocol and then finally your application layer protocol. No, you just put your application layer protocol right on top of probably TCP, the transport layer protocol. So this mirrors pretty closely how the standards work in the real world. So to review this, the IP model is the network access layer, the internet layer, the transport layer, and then the application layer. It's got 4 layers. However, nobody ever really refers to it. Everybody refers to the OSI model. So when you go to memorize these for your exam, know them both. But for the real world, really memorize the OSI model, even though it's not quite as practical. And you need to memorize those numbers. So you need to be able to say layer 3 and know that you're referring to the network layer. And if you hear somebody say, oh, it's a layer 7 protocol, you'll know that it's a top-level application layer protocol. So memorize those OSI layers and names. Now let's go over some really high-level network topologies. And this is largely a terminology exercise. Like, I want you to know when somebody says it's a mesh architecture or it's a bus architecture. I want you to know what that means. And you might also see things like this on the certification exam because they're easily testable. And people who write test questions tend to be lazy, so they like to go for really objective types of tasks to test you on. Up first, we have the classic star architecture. And in the star architecture, you take a bunch of devices, computers, hosts, routers, and you all plug them into one central device. So in the Ethernet world, the central device is a hub or a switch, and all the devices are just connected with an Ethernet cable. In a star architecture, hosts don't truly communicate directly to each other, at least not at layer 1 and 2. Instead, they're communicating with the central device, and then the central device repeats or forwards the signal as necessary to the destination. Imagine that you're sending a SMS, a text message, to a friend. Your message doesn't go directly to their phone. Instead, it talks to the cell tower, and the cell tower figures out where your friend is and then sends a message to them. That's a star architecture. Token ring is an interesting example, and I'll show you an example of how token ring works logically later. But physically, with the token ring, you plug all the computers into a central host. Logically, it doesn't quite work that way, though. In a bus architecture, a bunch of different hosts are connected basically to a single wire, so they literally receive a single electrical system. In a star architecture, there's an electrical device that's repeating signals, so it might behave a lot like a bus, but there's still something that's repeating it. In a bus, it's just one cable and everything's connected to it. So because there's no single device managing communications, it can be difficult to manage, because imagine that you had one host who just flipped out and just started broadcasting stuff across the network without waiting for collisions or following any protocols. It could take the whole line down. It would be like if you were having a quiet dinner conversation and everybody was politely taking turns speaking, and then there was a kid who just started screaming at the top of his lungs. Nobody would be able to continue the conversation until you had quieted the kid, right? Well, this happens in networks too. And with the bus architecture, you need to go to each of the different computers and figure out which one is malfunctioning and unplug it. And then suddenly everything starts working again. Nowadays, bus architectures aren't that common on LANs, at least, though I do have a bus architecture here at my house. I have home Powerline Networking. You basically just plug network adapters right into the power outlets of your house, and then they broadcast across all the electrical wiring in your house. Well, it's a shared media. It goes to every electrical outlet in the house. It doesn't go to a central hub where it gets repeated. So that's technically a bus network. Cable networks are also bus networks. If you're watching your local news station on cable, well, your cable company isn't really streaming that specifically to you. They're not like, oh, this guy wants to watch the news. Let's start it now. We'll set up a session just for him. No, they're broadcasting it out to everybody. It's a single electrical signal going out on this wire, and everybody who receives it receives it. You'll have an adapter at your house that's receiving all the channels all at once, all the time. And this cable box will just separate out the channel that you want to watch. But the rest of them are still coming to your hosts. That makes it a bus network. In a ring topology, each device is connected to two neighbors, and each of their neighbors is connected to one other neighbor, and it comes around in a full circle. So ring topology is really just a bunch of one-to-one connections that are chained together. And a ring topology can tolerate a single failure without losing end-to-end communications, because if you can imagine, if this guy falls off the network, well, this guy could still talk to the printer by going around the other direction. Like this, it would be shorter to go this way. But if he's offline, all right, we have to go through a few more hops, but we can still get there. Nowadays, the most common example of a ring topology is FIDI, which is a fiber optic communications usually used for communicating between hosts and storage. However, token ring operates logically at this level. I mentioned token ring is physically a star network. You would plug all of the hosts into a token ring switch, but logically the way it works is communications would travel from one device to the center, and then to this device, and then here, and then to this device. So nobody has used token ring in forever. I've literally never seen token ring, and I started networking in like 92 or 93. It was Ethernet even then. But it's still one of those things you see on the tests, and they specifically name it in the Sscp certification objective. So I want you to be familiar with how token ring works, even though I think it's mostly historical at this point. In a mesh network, everybody connects to everybody. Therefore, it can tolerate any failure, and anybody will be able to communicate. You have kind of the best performance possible, because if this computer here wants to talk to this printer here, well, it's got a direct wire. Nobody can interfere with those communications. You don't have to wait for communications to be passed. There's no need to worry about collision detection. You just have a direct link to anybody that you want to talk to. However, we don't really see mesh networks implemented in the real world all that often, because, well, that would be a lot of cabling. If you can imagine, if you had 10 computers in your organization and you had to draw an Ethernet cable between all of them and the printer, and then all of them and each other, it would end up being a lot of cabling and a real mess of wiring. So mesh networks don't make a lot of sense. Ad hoc wireless networks work like this. Now, ad hoc wireless networks are Wi-Fi networks, but you don't have a central switch. In an ad hoc network, everybody talks directly to each other. And because there are no wires, it's not a pain to connect everybody. The only other example I could come up with is internet backbone networking, and it's not a true mesh, but if you look at the tier 1 internet service providers, these are the biggest internet service providers. I worked for one for a long time, and we all connect into each other pretty much directly so that we can send communications from somebody's home network to the web server that they're trying to reach as efficiently as possible. So it's not a perfect mesh. Not everybody has a connection, but pretty much all the tier 1s have a connection, and the tier 2, the smaller ISPs, connect to several different of the tier 1 ISPs usually. So far this lesson has been very logical, very high level, very conceptual. I'm going to get a little more practical and a little more realistic and dig into IP addressing. IP addressing is the addressing that's used on the internet every day. This is what allows your web browser to find the web server and communicate through the hundreds of different switches and routers and cables to find a host anywhere in the world. It's pretty remarkable, and the secret to it is this block of 4 numbers like you see here. This is one of several different IP addresses used by the trainsignal.com domain. And you can see it's broken into 4 octets, and each one of these 4 octets can be a number from 0 to 255, though some of those numbers are excluded. IP addresses have 2 parts. The first part is the network address, which works like your street name, and the second part is your host address, which works like a house number. So you might imagine that these first 3 octets would be the street name, the network name, and it would take you to a specific network somewhere in the world. And then there could be up to 255 hosts attached to that network. The particular web server that we're looking for has an address of .28. So as the routers are sending your packets forward to the destination, they just need to look at the network number. Once that last router finds the LAN that you've sent your packet across the world to find, it just needs to look up the host number, which would be .28. Now, here's the magical and confusing part about IP addressing. The network and host number are variable. The network isn't always the first 3 blocks, and the host number isn't always the last block. It's defined by the subnet mask. So these are common subnet masks down here at the bottom. The subnet mask 255.255.255.0 is called a Class C subnet mask, and this is what you'll see almost all the time. And it means the first 3 octets of the IP address are the network address, and the last is the host address. If you look at the subnet mask, you'll see it's made up of 4 numbers, just like the IP address is. And if a particular number is 255, that means that number maps to the network rather than the host. If a particular number is 0, it means that that number maps to the host. If you have what's called a Class B subnet mask, such as 255.255.0.0, that means the first 2 numbers in the IP address map to the network, and the last 2 map to the host. And finally, a Class A subnet mask, such as 255.0.0.0, means that the first number in the IP address maps to the network only. The last 3 map to the host. We'll dig into that a little bit more. Now, you might have noticed that I've been calling each of these numbers from 0 to 255 an octet. Octet means a number that's composed of 8 binary bits. I'm going to hope that you have some familiarity with binary math already because I could teach an entire course in it. But here I've given you some examples of binary. Now, this is a block of 8 zeros. That's an octet. Each binary number can be either a 0 or a 1. It's basically like counting. If you only had 1 finger instead of 10 fingers, you would only count zeros and ones. And binary is the language of computers. This system of math was invented by a brilliant man named Boole, and we still call it Boolean math, though binary math is another common term for it. So if you look at the octets in decimal form, I told you that 255 meant that that number was dedicated to the network, and that was kind of a simplification. It is true, though. In binary math, in Boolean math, 255 is equal to 8 ones in a row, and 0 is equal to 8 zeros in a row. So if you look at each of the octets in an IP address, you can see that it could be broken down into 8 binary bits. If the subnet mask is 0, it would mean that all of the binary bits were the host address. And if the subnet mask were 255, it would mean that all the binary bits were the network address. And that is the most common way to express networks. But you can also break down an individual octet and split it between the network and host. So if you make the first 2 ones part of the network address and the last 6 zeros part of the host address, you'll end up with that octet of the subnet mask being equal to 192. If you dedicate half of that octet of the subnet mask to the network address, you'll end up with that subnet mask being 240. So the point I want to make is that the subnet mask and the IP address aren't really decimal numbers as you see them, like 184.106. They're actually a long string of 32 ones or zeros. That's the theory, and it's important for you to understand for certification exams. However, in the real world, we pretty much just deal with the decimal numbers, and subnet masks are usually 255 or 0. Sometimes a network administrator needs to divide up an existing subnet into 2 different subnets, in which case they'll use a subnet mask like 192. So they might specify a subnet mask of 255.255.255.192 instead of .0. And that would give them 4 possible networks within that single Class C network. So this brings me to the point of this slide, which is short network notation. Instead of writing the IP address 184.106.104.38 and then the subnet mask 255.255.255.0, you can use short network notation, which is to specify the number of ones in the subnet mask. So each one of these is 8 ones. Each 255 represents 8 ones. We have 3 sets of 255. 8 plus 8 is 16, plus 8 is 24. Therefore, we can just add a /24 to the number of the network. Here we have 2 octets that are all ones. That's 16 ones total. So we just add a /16 after the network number. And if you just have the first octet, 8 ones, you can just write /8. Again, you don't have to divide these up in groups of 8. You could have a /12 or a /18. You have a lot of flexibility there. However, in common practice, most organizations simply get Class C networks with a /24 assigned to them by their internet service provider. That's who will typically give you ranges of IP addresses. So you just use that /24 network and assign it as you will. There are only a few organizations that have Class B or Class A networks with /16 or /8. And these are typically big ISPs, places like my former employer, BBN, which is no longer around, unfortunately. Because we helped develop the internet and invent it, we were kind of the first in line to get these big blocks of networks, and so we did get big Class A's and Class B's. But a typical organization coming up online now is just going to get a Class C or 2 assigned by the ISP. So 32 bits of IP addressing is a big number. That gives you about 4.3 billion different IP addresses. And at the time that our founding fathers developed this IP addressing technique, that seemed like more than enough. They couldn't imagine needing more than 4.3 billion addresses. But that's kind of like the famous Bill Gates quote where he said, "Oh, no computer will ever need more than 256K of RAM." And turns out, yeah, we needed more than 4.3 billion addresses, especially considering so many of them are wasted. Most IP addresses get assigned and never used because the way the addressing space is divided up just isn't efficient at all. So there are not enough public IP addresses for every computer on the internet to have one. So we end up reusing IP addresses. That sounds crazy because everybody teaches you every computer on a network must have a unique IP address, but really you just need to have a unique IP address in your own network, like within your own organization. If you communicate on the public internet, you have to have one of these publicly assigned IP addresses, but every host on a network can use the same public IP address. This is a process called network address translation that I'll describe a little bit more later. But as long as we're on that private network, we might as well assign private IP addresses. And every organization is going to use these same 3 blocks of private IP addresses. The ranges are 192.168.0.0 to 192.168.255.255. And if you remember your short address notation, that's 192.168.0.0/16, because we have 16 bits of the network address. Another private address range, which isn't frequently used for some reason, 172.16.0.0 to 172.13.255.255. The short address notation for that is 172.16.0.0/12. I told you they didn't all have to be 8-bit boundaries. And finally, we have this big Class A private network, which is commonly used, 10.0.0.0 to 10.255.255.255. That's a /8 network. You can use the entire 10. whatever IP addressing scheme on your private network, as long as you have a network address translation device, a router, basically, that will give you a single IP address. You could have millions of hosts on your internal network all sharing that one IP address, at least in theory. So now let's dig a little deeper into network address translation, the technology that allows us to use these private IP addresses on the public internet. So here in the left corner we have the public internet. And every device on the public internet, if it's going to communicate with anybody else, it needs a unique IP address. That's the only way you can find it. So a Nat device is basically a router, and it has one public IP address. It uses that public IP address to communicate on the internet, and when it sends a message to a website, it has its public IP address in the source IP address field in the packet. And when it receives a packet, the response with the web page in it, it has its public IP address listed as the recipient of the packet. Now what the Nat device is doing is it's taking messages from all the hosts on your internal network and sending them out on the internet. It's basically acting like a proxy. It says, oh, okay, you need to talk on the internet? Well, you can't do that because you have a private IP address. But I'll take your private IP address, I'll package it in with my public IP address, and I'll send it out on the internet and then wait for the response. And then when the Nat device hears back, it says, oh, well, this was actually a message from the computer at 192.168.42.3. So I'm going to take out my own public IP address and put its private IP address back in. That's all a Nat device does. It just translates private IP addresses on your internal network to a public IP address on the public internet. And it works perfectly as long as all the hosts on the internal network are just sending out requests and not trying to receive incoming connections. Nat can, however, accept some incoming connections. Imagine that you have a big network filled with hundreds of different clients and they all need to browse Facebook and Reddit. Well, you can give them all private IP addresses and the Nat device will just take their connections and send them out to the internet. Because they're all outgoing connections, this one IP address is going to work fine. But imagine you also want to host an email server on your internal network. Well, the email server needs to be able to receive incoming messages. That's a connection coming from the internet and to the server. Well, the Nat device is really optimized to send out connections, but you can configure Nat devices to listen for specific types of connections that weren't previously requested and then send them to a specific host on the internal network. So email servers use the Smtp protocol, has a TCP port number of 25. If there's somebody on the internet that needs to send your organization an email message, it will look up the IP address of your email server and you'll have listed the it's called a mail exchange record, an MX record in DNS, you'll have listed that as the public IP address, not of your email server, because it is a private IP address and won't communicate. Instead, you'll have listed the public IP address of your NAT device. Now, the NAT device is just going to sit there waiting for incoming SMTP connections, even though it doesn't have an SMTP server running on it. It doesn't know how to talk email. But when it gets a connection using TCP port 25, it says, oh, that's SMTP, and I don't speak SMTP, but I know where the email server is. It's on the private network. So it just swaps out the public IP address for the email server's private IP address and forwards the connection on. So in this way, you can see NAT devices can accept some incoming communications. Basically, the NAT device needs to be configured for each different protocol. SMTP can go to the email server. HTTP can go to the web server on your internal network. One incoming connection per TCP or UDP port number, usually. Now let's talk about subnetting, which is the process of taking a big network and breaking it into smaller, little, more manageable networks. You perform subnetting for a few different reasons. If you were to put the tens of thousands of computers in an enterprise on a single network, well, that network would definitely get overrun. That would just be too many communications. Even with our modern Ethernet networks, there are a lot of what's called broadcast communications. And broadcast communications need to go out to every host on the local area network. So broadcast communications aren't all that frequent, but there are several different broadcast packets on the network every second. And your network can probably handle thousands of packets every second. But if you have tens of thousands of hosts connected to the same network, well, that broadcast traffic is going to overwhelm everything else. It'd be like if there was somebody just talking all the time, just yelling in a room, you wouldn't be able to have your own private conversations, right? Well, subnetting breaks that apart. So imagine that you're in a really big high school and all the students have lunch at the same time and there's thousands of students in there. The noise would be incredible, right? As they try to talk to all of their friends at the different tables. And nobody would even be able to carry on a conversation. It would get so loud that everybody would start talking louder and louder. Well, one way you could solve that would be to put up walls. You might put up one big wall and divide the room in two, and then you'd have half as much noise. But you might decide that's not enough, and you end up dividing them further and further, and maybe eventually you'd get to every table being in its own little room, in which case stuff would be really quiet, and communications would be really efficient, because it would be quiet, everybody could just talk to each other directly, and nobody would have to yell. Well, that's what subnetting is. You basically set up little walls between networks, and allow people to kind of communicate privately, and the broadcast messages don't end up causing too many problems. Of course, we have routers between those subnets, so if somebody needs to get from network A to network B, the router will say, oh, this is destined for a remote network, I'll forward it on. Routers, by default, don't forward broadcast traffic, so the broadcast traffic stops at the router. Subnetting also allows for delegated administration. In an organization, it's common to have somebody responsible for different floors of the building. So there's no reason you couldn't put all the floors in a single building on a single subnet, but you might break them apart into different subnets. That way, Mary can just be responsible for the second floor, and when Mary messes it up, she doesn't mess up the third or the fourth floor. So let's take a look at an example with actual IP addresses. Imagine you've decided to claim the entire 192.168 Class B network. That's about 65,000 different possible IP addresses. Maybe you actually have 60,000 hosts that you want to connect to your network. Like I was saying, you wouldn't want to put them all on one subnet, right? You could. In theory, you could connect them all and they'd all be on one subnet, and every broadcast message would go out to your 60,000 hosts. Well, it wouldn't be a very efficient way to do it. Well, a common way to do this would be to break them into Class C networks. Class C networks have the subnet mask 255.255.255.0. That's 24 bits of network addressing. And that gives you 254 hosts per network. So you could set up the accounting subnet with up to 254 hosts. Maybe they wouldn't need that many. You could have another subnet for the customer service, and another subnet for marketing. And if they use 10 of the hosts, well, you have some space to kill, right? You probably don't actually have 60,000 hosts. So it's okay if the subnet isn't completely used. You can have 4 hosts on a single network. Because it's private IP addressing, you can waste it all you want. Now I'd like to talk about a concept called the Demilitarized Zone, or a DMZ, also known as a screened subnet. A DMZ is a subnet dedicated to servers that need to accept incoming connections from the internet. So this is going to be your email server and your web server and your FTP server, your DNS server, any server that users on the internet need to connect directly to. Typically, even if you use private IP addresses, you'll use NAT and send those incoming connections over to your DMZ. The purpose of a DMZ is to limit damage during an exploit. Because these servers are on the internet, well, they have a much, much greater attack surface. While servers on your internet could only be attacked by hosts on your internet, servers in the DMZ can be attacked by anybody on the internet, which means there's a much greater chance that somebody's eventually going to break in. And what you want to do if somebody does break in is limit your exposure as much as possible, and the DMZ helps to do that. So imagine that somebody hacks into your web server and they take over administrative control over it from the internet. The first thing they're going to try to do is to get more control. They're going to try to jump to other hosts. They probably don't actually care about the public content on your web server, but they love to get their hands on your customer database, maybe with like credit card numbers, something you probably have hidden away on the internet. Well, if you set up your DMZ properly, they'll be walled into that DMZ and they won't be able to make the jump from your DMZ to your private intranet. There are a couple of different ways to design a DMZ, and this is basically a DMZ based on a multi-homed firewall. The term multi-home just means the firewall has multiple network adapters, and in this case you can see it has 3 network adapters. One that goes to your intranet just like any other firewall, but then it has this third one that goes to the DMZ, and the DMZ is this private little network for public internet servers. So you can see if somebody cracks into the mail server in this diagram, if they want to get to your protected network, they still have to go through the firewall. And presumably the firewall rules will be configured to block all connections originating from the DMZ to your internet, just in case somebody hacks something. The other architecture is this multi-layer approach. And in this multi-layer approach, you just have a second firewall that is dedicated to protecting the intranet from anything that might happen on the DMZ, and all communications come through the DMZ's network. So this helps provide a little additional protection. That first firewall on the internet, well, the firewall itself is exposed to the internet, and therefore it has a pretty big attack surface. What if somebody hacks that firewall? Well, of course, if they hack the firewall, they have a lot more power to gain access to the DMZ. You have to have that first firewall set up to accept incoming connections from the internet because it has to accept communications to the DMZ. But that second firewall can be configured differently. It can be configured with much stricter rules. Therefore, providing 2 layers of firewalls provides some defense in depth, what we sometimes call belt and suspenders protection. If you have an utter failure of the first firewall, that second firewall hopefully will protect you a little bit better. My recommendation is to use a different type of firewall for your second layer of firewall. Use a firewall by a completely different vendor. That way, if the first vendor has a security vulnerability that just got discovered and exploited, well, the second firewall vendor hopefully won't have the exact same vulnerability. So an attacker will have to figure out 2 different devices and how to bypass them. Another common use for subnetting is to create a quarantine network. Now, most home networks, if you plug an Ethernet cable in it, that computer's just on the network, right? You don't have to authenticate it in any way. Just if you can physically plug a cable into your switch, you have access to your home network. Well, many enterprises nowadays use what's called 802.1x to authenticate the actual layer 1 connection. So you plug a cable into a switch and the switch doesn't give you access to the internet. First, it needs to authenticate the client. That authentication can simply be making sure that the client has a valid certificate, meaning that it's been trusted to communicate on your internal networks. They might authenticate the user. They might require the user to put in a valid username and password for your own network. They might even check the health of the client. They could make sure that the client runs some anti-malware software and that it's up to date on the latest patches. So how does a lowly switch, a little device meant to repeat electrical signals, manage to authenticate people? Well, it doesn't. All it can do is pass on authentication requests, usually using a protocol called Radius, the same protocol used for dial-up servers and VPN servers. So basically, you just configure the switch to talk to your authentication server. This is probably a server that you already have running in your domain to authenticate users. You just point it back to that server, and anybody who connects to the network, well, it says, hey, you got to authenticate first, and then it forwards it on to the authentication server. And only when the authentication server says, this guy's trusted, let him in, does it actually attach that computer to the intranet subnet. What if authentication fails? What if the user doesn't have a valid password? What if malware has hacked their computer, or they don't have their patches up to date? Well, you could just not connect them to anything, and they wouldn't be able to browse the web or get any help, and then the user would end up frustrated, right? They'd be like, I'm trying to get work done here. I'm a valid user, but stuff isn't working. Well, maybe they'd find their phone and call IT, but even that would be a frustrating experience, and you'd have to open a ticket, especially if they just forgot their password, or they didn't get the latest updates because they were traveling and didn't have an internet connection. So what you'll normally do is attach them to a separate quarantine network. The quarantine network was where all the computers that fail authentication go. And on this quarantine network, you have a remediation server. And the remediation server has all the latest updates. How convenient. So if you get kicked off the intranet for not having updates, you get on the quarantine network, but there's a friendly server there that says, I can help you. Here are the latest updates that you need. Install these, and I bet next time you authenticate, you'll get connected to the intranet. The remediation server will also have self-help stuff. Maybe it allows you to reset your password. Maybe it just tells you the phone number for IT so you can get some more help. All right, who loves memorizing acronyms and numbers? I know I do. Well, the Sscp certification exam objectives want you to know some common protocols and ports. And you know what? It is useful for the real world. It's helpful when you're talking to your peers. Somebody will refer to port 80, or they'll refer to HTTP, or they'll refer to web communications. You need to know that all those things are the same thing. So I'm going to round up some common protocols and ports. Ooh, look at this slide. That's a lot of information. You know what? Why don't you take a picture of this with your phone, and then when you're waiting in line at the ATM or something, you can go back to it, and it will help you memorize this sequence. For most people, the best way to memorize a table of information like this is repetition. And for me, I've been doing this in the real world long enough that I had these memorized just because I had to go configure firewalls for DNS on port 53 over and over again. And I actually connected manually to port 25 when I was testing Smtp server. So you kind of learn these in the real world over time as a network administrator or as a security guy. But as you're ramping up for the Sscp certification, it would be really helpful if you had this chambered in your brain. Telnet is a TCP protocol, uses port 23. You'll find almost everything nowadays is TCP, so if you're not sure, it's a good guess. Basically, the only thing that's not TCP is DNS. That's a UDP protocol. Streaming video and audio is also usually UDP based. TCP is a connection-oriented communications. It's reliable, so if a packet is corrupted, it's retransmitted. UDP is not reliable. If something gets corrupted, well, the application could decide to retransmit it, but the layer 4 communications don't. So if you imagine that you're watching a live video stream and one packet of voice data gets corrupted, well, it doesn't have time to retransmit it. By the time your computer could send a message to the server saying, hey, I missed that vowel, the server could retransmit it, but then it would be way too late. So usually with things like streaming audio and video, you use UDP because it's a tiny bit faster, and you're not going to bother retransmitting anything anyway, because it's better just to leave that person with a bit of silence or a bit of static and continue on with the broadcast. But for things like sending an email message, you wouldn't want half your email message to be garbled. So SMTP, the Simple Message Transport Protocol, uses TCP because you don't want your mail corrupted. But your video stream, not a big deal. SMTP uses port number 25. HTTP is used for web stuff, and it's port 80. That's really, really common, something that's really important to know. Port 80, web stuff. Jumping down a little bit, HTTPS, that's secure HTTP, uses port 443. So those are probably the two biggest ones that everybody needs to know. 80 for web, 443 for secure web. Another mail protocol, POP, a post office protocol, is used by email clients to retrieve mail from the servers. It uses port 110. SMB is server message block. That's the name of the protocol, and it's used for file sharing across networks. And it originally came about in the Windows operating system, but nowadays all operating systems support file sharing with SMB. It uses TCP ports 139 and 445. Ldap, the Lightweight Directory Access Protocol, can use both TCP and UDP, though I think in practice it uses TCP far more than UDP. This is how you find other users on your network. This is how you find the closest printer. It's a directory protocol, so you can find things. It uses TCP or UDP port 389. There's another SMTP protocol, a slightly newer version, that uses TCP port 587. And then if you ever use remote desktop or terminal server, that uses TCP port 3389. And finally, another really common protocol on home networks is UPnP. This is how a computer on the home network can tell the firewall that it needs to be able to accept, say, an incoming Skype connection directly into it. The firewall would normally block incoming connections, but UPnP configures it to make it easier for connections to come in, and it uses TCP port 5000. This is Tony Northrup for Train Signal, and thanks so much for watching this video lesson.